Hi, welcome to Solideo Gloria Physical Chemistry. This is a lecture series of chemical kinetics. Especially we will be focusing on how to deal with a system of chemical reactions. So today is an introduction, and also today we are going to talk about a little bit a kind of introduction of matrix equation for chemical reactions. Well, this is not exactly a topic for chemical kinetics as it per se, but I think that this is rather important or to know when you are implementing a set of chemical reactions in a computer code. So let's begin. By the way, this lecture series will include three parts. This is the first one, introduction. Second part is about gathering chemical information, that is in this case rate constant and maybe activation energy from various sources like simple collision theory or transition state theory like that. And third part is to go over differential rate law, which is how the rate of chemical reaction depends on concentrations to be integrated into the integrated rate law, which shows you the concentration as a function of time. And then as time permits, we are going to implement or utilize a Python program to solve a set of linear differential equations, which is differential rate law. Okay, let's begin. Okay. Well, just a kind of just a view of a chemical laboratory. I think that I recall this like 1983. I visited a lab in University of Texas at Austin. The late Professor William Goddard chemical kinetics lab. This is a view of shock tube. Shock tube is kind of an experiment. There is a schematics like here. So there is a kind of tube, very long tube. Like I remember it was something like 10 meters or so. More, maybe longer, and then diameter. This one is very. This one is really big one. It's more than like 12-inch diameter shock tube. Correction. This is not from Bill Gardner's lab, but anyhow, this is the same kind of shock tube. So how it works is that you have a driver section. Okay, this is a kind of gigantic tube and driver section here, and then we put a diaphragm or kind of a block in the A section, like here or here on my laser pointer, and then we pressurize it with high pressure of driver gas. Driver gas would be just inert gas like argon, something like that. So at high pressure with the diaphragm compartment in A side, and then this is the driver section. This is kind of long part of the shock tube, probably from here up to here, something like. And then there is a diaphragm at the back. So it is pressurized in this part of A part, and then we have some reactant mixture here in the driven section, and then there is a test section. At the end there is a kind of small window here, and then source and the detector. It's a kind of doing a laser spectroscopy or some kind of spectroscopy. Either they monitor some intermediate species or the product species like that. And then there is a kind of and also all systems are evacuated, and then the last part is just a kind of collection of the waste. Okay, so this is a kind of very simple reaction. It can be done here. So in the driver section, driven section, and we put some mixture of argon and I'm sorry, methane and oxygen, and then argon in the driver section at high pressure. At some point, you know, how do they do that? Is they have a foil, and then they scratch like many times, something like 3 times, 4 times this way. It's a kind of art. So they put that scratched foil here, and then with enough pressure, it will rupture. And this side is, the other side, driven section is in a kind of vacuum with very low pressure of reactant gases. Okay, then this is a sudden rupture. This driver gas at high pressure is kind of expanded in a way. So it is a kind of adiabatic compression is done in this way in the test section. So the shock moves from left-hand side to the right-hand side. Actually, in your case, you go that way, left-hand side to right-hand side, and then it is adiabatic compression and raise the temperature. It is amazingly, you can obtain amazingly high temperature, so that you may obtain the information about this methane oxidation or methane combustion reaction, methane plus O2 making CO2 or H2O, like that. This is a kind of very simple representative reaction you may observe here. In fact, this kind of shock tube experiment is for something like this. I kind of copied this kind of scheme, reaction scheme, from William Gardner's paper, very old paper, 1982, Scientific American. The title was like flame, or some chemistry of flame, something like that. So this system is C1 and C2 hydrocarbon oxidation at high temperature. So high temperature means that something like 3000 K or 5000 K, like that. I'm not sure about that. I don't know exactly the detail, but high temperature produced this kind of very short time by the shock tube expansion, which is adiabatic compression. So it raised the temperature at the shock end. So basically, C1 species is methane and C2 species is ethane. How they connected is the methane, first of all, at the first step, it generates a methyl radical, and then methyl radical with oxygen could be converted to methoxy radical or formaldehyde, something like that, and then later on is CHO radical and carbon monoxide. And also ethane will be easily is broken to methyl radical and thus follow the same steps. And then methyl radical, it could be combined or capture methylene group to make ethyl radical, or ethyl radical is also produced from ethane. And then that ethyl radical will be oxidized with this species, and then then eventually carbon monoxide. And then ethane molecule could be dehydrogenated to ethylene, and then another step of dehydrogenation will be producing acetylene. And then acetylene also could be, make acetylene radical or oxidized, and then methylene group and carbon monoxide. And then this methylene group could be reacting with methyl radical to make this species and ethyl radical species, like that. So this is a kind of very complicated or complex system of reactions. So today's topic is how to deal with this type of chemical kinetics. I assume that you have been through with chemical kinetics, either gas molecular kinetics, molecular gas kinetics, and also chemical reactions, kinetics of chemical reactions. So chemical reactions in general chemistry level at least, so that you know how to integrate your rate equation, first law, second law, Zero's law, and also the kind of topics for half-life, like that. So, but this is a kind of a little bit advanced for our graduate student, then, so that they I just let them handle this kind of complex reacting system or complex system of reactions. Okay, so this is basically our topic in the kinetics series of kinetics, chemical kinetics lecture. So here, two reactions may for methane and ethane reaction, we just make in an elementary level, or in general chemistry, we just to write the stoichiometric equation just like that. Methane oxidized to carbon dioxide and water. Ethane also oxidized to the carbon dioxide and water with this stoichiometry fulfilled. And then those things, those stoichiometry equation, but this system of reactions, even it doesn't show you carbon dioxide yet, eventually it will be included. But at the Bill Gardner's idea was, I mean, in this case, was just explain how the flame works. So probably it's not there yet. But anyhow, the stoichiometry tells you these two equations like that. So this kind of stoichiometric chemical equation could be written in this way: B is a chemical species, and N is these stoichiometric coefficient. In this case, positive stoichiometric coefficient for the product, and for the reactant, those stoichiometric coefficient is given as negative number. Okay, and also in order to express the rate of the reaction in a kind of in the equal ground, we define the extent of reaction, how much the reaction progress is that with Xi. Xi is equal now is used in this case when species I has original or initial condition for the initial amount for the species I is Ni naught, and then if there is a reaction proceeds, then the reactant, the extent of reaction is Xi, and then it is multiplied by its own stoichiometric coefficient. Okay, then that is the current amount of species I. Now the rate is determined in terms of dN dt, okay, as a kind of differential. And dN dt, if you look at dN, is nu d Xi. So dN dt is nu d Xi dt. And the rate is, in terms of rate, is that this d Xi dt is the extent of reaction per time is d Xi dt, and then over the volume. So this is a kind of chemical reaction rate. Sorry about this. This is actually V, and that is Ni in Greek. And now if you see this equation carefully, then d Xi dt is equal to 1 over Ni and dN dt. So 1 over Ni dN dt and over V. And if you look at this, dN over d over V is actually the concentration. So rate is 1 over stoichiometric coefficient and d species dt. Okay, so that is, we define the rate. And then the rate law or differential rate law told you, kind of states that the rate itself is a kind of function of concentration. The dependency on the concentration is expressed by the order of the reaction. So in this case, there are two species here, Bi and Bj. So in this equation, the rate is alpha's order for Bi and beta's order for Bj, and then Bi, Bj, the overall order of the reaction is alpha plus beta, and then this proportionally constant is the rate constant. So this is kind of elementary expression for the chemical reaction rate. Okay, so that's what I said. What I said is that you have pretty much covered about this basics of chemical kinetics in your previous lectures, like general chemistry or physical chemistry, the first part. So, so our goal is to handle this type of complex system of reactions, incorporating these ideas. Okay, so there are two things, kind of elementary ideas in chemical kinetics, is that for chemical reactions, we are going to talk about actually two things: mechanism and rate. So rate we have been talking about in terms of concentration, which is the differential rate law. And then if when we integrate the differential rate law, we'll obtain, that is integrated rate law, which is the concentration as a function of time. Okay, and then second part of the elementary chemical kinetics, the mechanism. Mechanism is a sequence of elementary steps that add up to give the overall reaction. So which must explain also the rate law and also kind of some kind of collection of chemical evidence in such a way that intermediate or equilibrium, just like that. Okay, and the molecularity is for the elementary step. So how many molecules are involved in the elementary step as what? Reactant side. So unimolecular, one molecule, bimolecular, two molecule, timolecular, or trimolecular, three molecule are involved in the elementary step, meaning as a reactant. Okay, so in a kind of diagram, how do they do in chemical kinetics or kinetics for reaction, is that they propose or kind of assemble the idea into a mechanism, which I said the sequence of elementary reactions. And then this, based on this, we'll write a set of differential equations. And then of course we incorporate the conservation equation, which is the stoichiometry relationship. And then usually this could be done, the set of differential equation, the set of differential equation, which is the rate law, differential rate laws, which will be integrated. Either way, you can integrate by hand, analytically, or using computer numerically. So in either way, you would obtain the integrated rate law, so which is a concentration as a function of time. But when you do, or even you do numerical integration, you might utilize certain type of approximation. One kind is the steady state method, and the other one is that assuming rapid equilibrium among reactions. Okay. So this is basic scheme in your chemical kinetics idea, and we expanded to cope with complex system of reactions. Basically, we are going to model a complex system. So there are many, we have seen the methane and ethane combustion or oxidation at high temperature. There are many reactions are involved in there. So that we call a complex system of reactions, and how this is schematics of how the kind of procedures, how these work together. So at the beginning we said that system of reactions, so that is a series, just very similar for one reaction, single reaction, we say mechanism. Here we say system of reactions, which is the series of elementary reactions. Okay, and then that should yield you or mapped into a set of differential equation. That's the same part, but here you have many reactions here. Not element, the series, which was for the mechanism was the series of elementary steps, but here elementary reactions. So reactions may involve more steps inside. And then we have set of differential equation, and also we have to incorporate the conservation equation for the stoichiometry relationship, and then that is integrated to yield you the concentration could be monitored as a function of time. Okay, so here we also, in order to solve the differential equation, there are some chemical informations required, which is a set of rate constant for each elementary reactions, or for each elementary steps we need the rate constant. The rate constants could be obtained from experimental data, meaning is that if you have run similar experiment, for the same experiment for similar reaction, so the same reaction, you would obtain the rate constant for that particular reaction. Or some chemical data you can obtain from some chemical data, such as incorporating the obtain the activation energy from forward and backward enthalpy of reaction. Then you might obtain that activation energy. Then from the activation energy you obtain rate constant from out of the Arrhenius equation. And also theoretically you can obtain the rate constant from collision theory, or just by doing quantum and statistical mechanical calculation, theoretical calculation, and transition state theory you may obtain the rate constant. So that gathering or incorporating all these idea into the rate constant, and then by incorporating the stoichiometric relationship, you derive to solve the set of differential equation that will yield you the concentration as a function of time, and then that could be also monitored by your own kinetics experiment. So with the experimental data, it feed back into the experimental data, and then with using the experimental data you remodel or modify your model in the set of differential equation or rate constant even, and then this kind of matching with the experiment, compare with producing your integrated rate law, and then match with compare with the experimental data, and you find out what is going on actually. So what is then you would understand how the system of reaction work. Okay. So that is basically the scheme here. So today, this lecture will concentrate this one and that one. So conservation equation, although that's not directly the kinetics material, we are going to present that matrix equation for set of reactants. And also probably this is, I just skipped it, but we just did one example for experimental technique, which was we just talked about shock tube. Okay, so matrix equation for chemical reactions. Well, first of all, this is not, as I said, directly a material for the chemical kinetics. Chemical kinetics, you may have even competing equation or several similar set of equations to do kind of from reactant to product way progress. So, but here we are going to identify a set of independent chemical equation. What does it mean by independent? Meaning is that if there are series of reactions, if two or more other reactions could represent the reaction, then that is not independent. Okay, so no member of the set of the set of chemical reactions, no member of the set may be obtained by adding and subtracting other members of the set. That is independent chemical equation. That set is independent in that sense. So usually this number of independent chemical reaction is equals to number of species minus that number of independent reactions. That's kind of a component. So the number of component is the total number of species minus number of independent chemical reactions. That's the kind of relationship for chemical stoichiometry or chemical equilibrium, like that. So for a general chemical reaction is written in this way. So positive coefficient for the product, negative coefficient for the reactant. So for example, in this case, CO plus half O2 molecule equals to, it's a kind of carbon monoxide oxidation reaction to CO2 carbon dioxide. In this case, we could write it in this form: minus 1 CO minus 1/2 O2 plus 1 CO2 equals 0. So sigma di bi equals 0 form, just like this. Then out of this we can write what? We can write chemical equation in such a way that a kind of vector form, a molecule, a species in a vector, and then the stoichiometry equation is written as a vector sum of vector, just like this. So for example, CO has 1 carbon, 1 oxygen, so it's a column vector 1, 1. Oxygen is just O2, no C2 oxygen, so 0, 2 is a column vector for O2. CO2 is 1 carbon, 2 oxygen, so column vector is 1, 2. So CO is 1, 1, O2 is O2, 0, 2, CO2 is 1, 2. That represent its chemical species. And these column vectors are combined in this way with the stoichiometric coefficient for minus numbers for reactant and plus number for the product. And then that is identically equal to 0, so it is kind of equal to null vector. So in this way, this is a way we can write stoichiometric equation. And then that stoichiometric equation, if we put these columns together in the chemical species in order, could be written as a kind of column vector side by side as a matrix, form a matrix, like 1, 0, 1, 1, 2, 2 matrix here. So those are this species matrix in a way. And then we can write down another column vector, in this case, with the stoichiometry coefficient, minus 1, minus 1/2, and then plus 1, and then that is equal to null, 0 vectors, 0 vector, because in this case. Yeah, so when you do this matrix multiplication, 1 times minus 1, 0, 1 times plus 1, so minus 1 plus 1, 0. So that is if you multiply this matrix by this column vector, you will get this 0 vector. So this is one representation, or one way to represent the chemical equation. Then question is how you obtain this stoichiometry given this and this and that species. Meaning is that when you are given with, okay, in your reacting system, while it's going, or from the beginning, or whatever end of the reaction, anyhow, it's a kind of reaction mixture. You will find, if you find carbon monoxide and oxygen and carbon dioxide, what is the stoichiometry equation, or how many reactions are there, independent reactions there. That then the way we are going to talk about will tell you. So matrix equation is written in this way. You see, we have just seen this A times A, a matrix times Ni, a vector equals a null vector. So in this case, A is called a conservation matrix. Conservation meaning is that the species there, what species are there, or what species are found. Okay, so 1, 1 is what? Carbon monoxide. 0, 2 oxygen. 1, 2 carbon dioxide. So this is a kind of molecular species conservation. I mean, reactant as a reactant or as a product. So this A matrix is a conservation matrix, and then Ni was a stoichiometric vector matrix, or stoichiometric number matrix. Okay, or this is also called the null space of the A matrix. That's a kind of a mathematical term. And then 0 matrix, a null matrix. Okay, So this is connected in this way. I mean, we have just seen. And how you obtain from this conservation matrix the Ni, the stoichiometric number matrix, meaning is that this is a kind of in your general chemistry, this is kind of a balancing your chemical equation, but this is kind of fancy way. Yeah, exactly. You're doing balancing. You're doing the balance of the chemical reaction, chemical equation. But this is a simple. But when you are given with kind of complex mixtures, and then this is a way or systematic way, or you can implement as a computer code for solving this kind of in a second or so. Okay, maybe millisecond or so. Okay, so how we do that? So in that case, you have a conservation matrix from your kind of participating your reactant and product molecules or species, and then you do the Gaussian reduction of the A matrix into reduced row echelon form. Let me tell you what those are later a little bit later. And that is the null space, meaning is that stoichiometric coefficient. How it does? Okay, so reduced low echelon form is just like this one. So 1 and 1 in the pivot in the diagonal form, and then the rest is this is the reduced row echelon form. I'm not. Yeah. So how you obtain this by Gaussian reduction? In this case, in a matrix, you can subtract a multiple of, if you multiply a constant to a row or column and add it to or subtract to other column, and then that other column, but that does not change the kind of value or the kind of property of the matrix, right? So what you do here is that first row, second row, what you can do is that you just subtract the first, leave the first one, 101, 101. But from the second row, you subtract the first row, what you get. So 1 minus 1 is what? 1 minus 1 is what? 1 minus 1 is 0. Yeah, 0. And 2 minus 0 is what? 2. 2 minus 1 is 1. So you obtain now 0, 2, 1. 0, 2, 1. And also, if you divide it with the same number, that does not change the property of the matrix. Maybe it's, yeah. So what you do is make half of it. So 0 divided by 2 is 0. 2 divided by 2 is 1. 1 divided by 2 is 1/2. Now what you have is 1, and so you have a row echelon form. When you obtain the row echelon form, you make the last column or the beyond the diagonal matrix. So this is, in this case, there is just one column, and then make a negative of it. So instead of 1, you have -1. Instead of 1/2, you have -1/2. And then you put 1, or in a case you do unit matrix actually. So for one element, there's 1 by 1 matrix. The one is the unit matrix. So now what I did is that I get this column and make a negative and put unit matrix. In this case, +1. So -1, -2, 1/2, and 1. You remember that these are the coefficient of the reaction. So CO plus 1/2 O2 equals 1 CO2. Okay? Yeah, just like that. So this is the way you obtain a set of independent chemical reactions given with that kinds of species. So with the species, you first construct the A matrix, and then you can obtain this stoichiometric number matrix that will give you what kind of reactions there. Okay, well, let's do some example like this. Okay, here, I think this is the last one for the short lecture. And okay, so in your reacting system, you find carbon monoxide, hydrogen, carbon dioxide, water, and methane. Okay, so you can construct, now there are element wise there are carbon, hydrogen, and oxygen only. So your column will be done in this way: carbon, hydrogen, oxygen. So carbon monoxide 101, hydrogen 020, carbon monoxide 102, water 021, methane 140. And then these columns will make this A matrix. So this is conservation matrix. And then we do Gaussian reduction on this A matrix in such a way that we'll obtain this one-on-one diagonal form. Okay, so this is actually type of unit matrix, but this is a row echelon form of this A matrix. And then what you can do is a kind of arithmetic, is that firstly you make what? Just divide by these two. Then what you get is 1, 0, 1, 0, 1. Just leave it and divide by 2. We'll get 1, 1, 2. Okay, and then automatically you have obtained this part. Okay, and then you wanna make this disappear. So how you do that? You subtract, maybe subtract from this line from this line. So, and then what you get, 0, 0. In this case, you leave 1 here. Okay, 1. And you subtract that, leave 1, you subtract that, minus 1. Okay, yeah, so just like that. And then, I'm not sure how you obtain this, but we have to remove this one. How you remove that? How, because it is 10101. How you remove this one? Because then you subtract. No, this is one half of this line from this. So 1 half 0, 1 half of 0 is 0, so you leave and these two. But no, so just subtract. Okay, subtract this line from the top line. So subtract was, yeah, it was 1. Okay, so subtract, if you subtract it, that's 0, and if you subtract it, you leave minus 1. If you subtract minus 1, it leaves in the case what you do is that 1 minus 1 is 2. Okay, 1 minus 1 is 2. Okay, yeah, so this is low echelon form. In this case, all ones and zeros and zeros. So the kind of unit matrix. And then this is your the rest of the coefficient, rest of the vector. And then what you do is that make a negative of all this, meaning is 1 minus 2 minus 1 minus 2 minus 1, just like this. And then you put a unit matrix for the 2 dimension is 1, 0, 0, 1. So you put the unit matrix. Then this is the first reaction, and then the second reaction for those in the same order, those chemical species. So for this one, for the first one, positive is for the reactant, product, and negative is the reactant, which is H2 plus CO2 equals CO plus H2O. So first reaction. Second reaction is that 2CO plus 2H2 equals 1CH4 plus CO2. Okay, 2 equations. Maybe so this is the kind of independent reaction, set of reaction representing this is one way representing the reacting system of these 5 species. Okay. So this is a way you can handle stoichiometry or conservation relationship with the given species. Thank you for listening. Kind of first lecture, and there will be 2 more chemical kinetics lecture to handle a complex system of chemical reactions. Thank you.